Hi everyone. In this lecture, we will try to understand the behavior of first order systems to ramp inputs. So first I'll start with the definition of a ramp input. So here a ramp input is one that increases linearly with time, and here the ramp is assumed to have a slope m. So if it's a voltage input, m will have a unit of volt per second, or if it's a current input, it will have an input of current per ampere per second, volt per second or ampere per second. So I'll start with a simple first order low pass filter. So with a DC gain h of 0 and a single pole at omega equal to omega p, a left of plane pole. Now what would happen when I apply a ramp input m of t into u of t to this system? So we will first convert this to a Laplace transform, which is m by s square. And when I feed this as an input, I can write h of 0 into m into 1 by s square. Okay, unlike a step input, here there is 1 by s square, so you'll have to apply partial fractions twice. So I'll first write 1 by s into this, and I'll take 1 by s common out, and we know how to expand this. So you'd get, now again when you take 1 by s inside, you'd get 1 by s square minus 1 by omega p into, again you would have a term 1 by s by omega p. So this I'll expand it using partial fractions. Again I would get 1 by s minus 1 by omega p into s by omega p. So the whole thing is multiplied by m into h of 0. So now if you take inverse Laplace transform of this equation, you would get m h of 0 into t into u of t. So now we know 1 by omega p is time constant for a first order system. So I'll write it in terms of time constant. Tau into 1 minus e power minus omega pt. It's actually t by tau, but it's understood. So now we already discussed how to plot this input. So I said first I'll just show how to plot this for the case when h of 0 is 1. It's easier to understand it that way. So your input has a slope of m. It increases as linearly as a function of time. Now if you look at this function, for t much greater than the time period, so I can ignore this term, and this function will reduce to t minus tau into u of t. So if I first plot t minus tau into u of t, so that is your input is delayed by tau seconds. So this is a line which is actually t minus tau into u of t. Okay, so this function will be what this function alone, I'm just this function will be at minus tau at t equal to 0. So but anyways, so the function would be like this, it will approach t minus tau into u of t. First if you look at this, at t equal to 0, everything, all these both these functions will be 0. So you will start from 0 and then asymptotically reach this value. So it's, in fact you can draw the two graphs and plot it. So one is a linearly increasing graph, the first term. The second term is nothing but an asymptotically rising input which rises exponentially to a value of tau. So when you take the difference between these two, okay, you will get this graph. Now the slope of this line will be m. Okay, here I've assumed h of 0 is 1. If h of 0 is not equal to 1, then your input will have a slope of m. The output will have a different slope depending on h of 0. It is m into h of 0. So in this case I have assumed h of 0 is less than 1, or your slope can be greater than 1. H of 0 can be greater than 1. So when h of 0 is greater than 1, you have a higher slope or you will have a lesser slope. For passive circuits, as we discussed, h of 0 is always less than or equal to 1. So the output will lie in this range. Okay, it will be between the input and the 0 line, assuming the gain is positive. So that's about a first order system. So what we discussed in the we already discussed about a ramp input to a first order system, a simple single pole response. So what we said was that the input is increasing linearly, and the output will look like, in the steady state it looks like the input and output are delayed by tau seconds. Okay, so if the input is m into t into u of t, your output would actually be, in the steady state, I'm plotting the steady state, t minus tau into u of t. In the steady state, difference between the inputs, a difference between the input and the output, the gap in the steady state okay, the gap in the steady state is actually m tau. Okay, so that's all about a first order system, ramp input to a simple first order system, first order low pass filter. So I'll just take an example of a problem which is a simple RC circuit. Here we know in this circuit h of 0 is 1, okay, and the input is applied as a ramp at this point. Now we know the instant the input is applied, the capacitor will behave like a short circuit. So both the input and the output will be at same voltages. Okay, but later once you're once the input starts progressing, what would happen is that even though the capacitor will, for high frequency input, the capacitor will offer very low impedance and most of the voltage will drop across the resistor, and we also discussed that it will generate a current which will be proportional to, which will be simply m into t by r into u of t. This is for very small values of t and when just the input is applied. At that point, this current will flow into the capacitor, and now voltage across the capacitor is integral of current. So for small values of t, the function will behave like an integrator. Okay, so the slope, if the input is raising with the slope m, the output will have zero slope because it's raising as t square, it raises as a parabolic function. So it will raise parabolically. Now we know the steady state value is actually t minus tau. So eventually if you look at it in the steady state, what happens is the capacitor impedance becomes very large. If the capacitor impedance becomes very large, then most of the voltage should appear across the capacitor. But then initially it was taking some time to build that voltage, so because of which there will be an inherent delay. It's not able to catch up. Both of them are increasing at the same rate. So if there was an initial delay between the two functions, that will persist. Okay, and we can also see if the voltage across the capacitor is a ramp from a circuit's point of view, that ramp voltage will demand a constant current, and that constant current will flow through the resistor, creating a constant voltage drop, and that voltage drop will be simply equal to m tau. Okay, so that way you can again see that both the input and the output voltage will always have a constant voltage difference of m tau. Here it's h of 0 is 1, so it is simply m into tau. Okay, so for a ramp input, your output will look like a delayed version. For large time constants, it will look like a delayed version of the input by tau seconds and delayed by tau seconds. That's the response of a first order low pass filter. Now we'll analyze the response for a first order high pass filter with a gain h infinity as the high frequency gain. Again, this function we have already drawn it, and if I show it on the Bode plot, it starts from minus infinity and eventually it goes to, at omega equal to omega p, it will be minus 3 dB. At high frequencies it will be h infinity. It's 20 log of h infinity. I'm just showing it as h infinity here. Essentially it is 20 into log 2 base 10 of h infinity, modulus of h infinity. Now this function, to find the step input, the response for a ramp input, I'll just express this as 1 minus 1 by s by omega p. Now when you feed a ramp input, which is m by s square as an input to this, we have already derived the expression for this, so I'll directly write the time domain output. So this would be h infinity, the first term will lead to h infinity into m t into u of t. The second term is a low pass response, so I'll take h infinity common out. I'll get minus m into t into u of t minus tau into 1 minus e power omega pt into u of t. Okay, so this function, when you take this negative sign inside, these two terms will get cancelled, and finally will be left with h infinity into m tau into 1 minus e power minus omega pt into u of t. So this expression, if you see, there is no ramp in this expression. This is simply a term which would asymptotically rise and reach a steady state value, exponentially rise and reach asymptotically a steady state value of h infinity m tau. Okay. Now if you look at your input, it's a ramp. Okay, it's actually a ramp. Let me plot this in a different graph. The input is actually a ramp, but the output with a slope mt into u of t. Here I'll assume the h infinity as 1, just for illustrative purposes. It's easier to show it that way. The output would reach a value of m tau in the steady state. Okay. Now even though the input is reaching infinity, the output is reaching a finite value. Now if you look at the transfer function, it is s by omega p by 1 plus s by omega p. I have assumed h infinity as 1 for the time being in this circuit, in this system. So now we'll analyze the input for sudden changes, that is your input at t equal to 0 and t equal to infinity, for t much greater than tau. Now first we'll analyze at t very close to 0, which is your input is suddenly changing, so it's like a high frequency input. So whenever the input is high frequency, I can ignore 1 here. This term will be dominating because omega is very large, s equal to j omega. So I can ignore 1 and this term will tend to 1. So therefore for h infinity equal to 1, the case both the input and the output will be same at t equal to 0. When if you remember a low pass filter, the output was rising parabolically, it was behaving like an integrator. But here this system will behave like a system with a constant gain at t equal to 0. So you will just, output will also be a ramp. It will try to approach like a ramp at t equal to 0. In the steady state, which amounts to lower frequency response, this function in the steady state, your omega is much smaller than omega p, so I can ignore this term will be ignored, and this function will simply reduce to s by omega p or s tau. So it behaves like an ideal differentiator. Okay. Now you have a function mt into u of t. If you differentiate this, pass it through a differentiator of this form t dvi by dt. No, that's the time domain expression for this. When I pass it through this, the output will be m tau, and that's what you're getting here. Okay, in the steady state, it's behaving like a differentiator, and the output will be m tau. Initially, it's just a system with a gain of 1. Now what happens if you look at it? The input actually at t equal to tau, the input reaches the value of m tau. That will be the steady state. I mean, the time taken for the input to reach the steady state value of the output is simply tau, t equal to tau. Okay, and if you look at the final steady state error, it will be infinity. The output error diverges. Okay, because the output reaches a constant value, the input will keep on increasing, and so the error will diverge. But this is a system. I mean, it's a low pass filter, so it's high pass filter, so DC gain is 0. So the system will not actually track the input. Okay. So that's about a system's response to a high pass filter, a first order high pass filter. So now if we'll take a circuit. So the transfer function for this is src by 1 plus src, pole is at 1 by rc, or time constant is 1 by p, which is rc. Now when you apply a ramp input, the instant you apply the input, the capacitor will behave like a short circuit, so the output will entirely appear across the resistor. Okay, so therefore both the input and the output are same at t equal to 0. After that, the capacitor would start slowly getting charged. In the steady state, the capacitor voltage will be a ramp, because it's going to take most of the voltage, and the resistor, because the voltage across the capacitor is a ramp, the current through that will be constant, and a constant voltage will be developed across this. Okay, so we can very easily see if m into t into u of t is the voltage across the capacitor, the current through the capacitor is mc. Okay, m into c is the current through the capacitor into u of t is the current. This is the steady state current. That multiplied by R will give you the steady state output voltage across the resistor, so which is nothing but m tau. So the steady state voltage will be m tau across the capacitor, across the resistor. Okay, and this is as predicted from the mathematical equations. Okay, so now we will go about analyzing a general transfer function of a first order system, which is with a finite 0 on the pole. Now this function, again, we have already written it as a sum of a high pass and a low pass transfer function. Again, this term can be written as h of 0 by omega z into omega p into s by omega p. Again, this term we called it h infinity and reduced it to h infinity. So it's written as a sum of a low pass and a high pass term. Now we know the ramp response to a low pass system. So that is simply, I'll directly write it assuming input as m into t into u of t as your input. The output would simply be h of 0 into m t into u of t minus tau 1 minus e power omega pt into u of t. Okay. Now the response of this time, this part of the input, which is your high pass input, would actually be h infinity into m, okay, into tau into 1 minus e power minus omega pt into u of t. Now I'll rewrite this expression. This expression can be rewritten as h of 0 into m into t into u of t minus tau m into h of 0 minus h of infinity into 1 minus e power minus omega pt into u of t. Now this term was same as a first order low pass filter, okay, but this term is different. You had no h of infinity in the previous expression which we derived a few moments ago for a first order low pass filter, but here there is also an additional term h infinity. Now h infinity is nothing but h of 0 into omega p by omega z. So if I write it in that form, okay, and then I'll take m into h of 0 common out, I'll be left with h of 0 into m into t into u of t minus 1 minus omega p by omega z into tau into 1 minus e power omega pt into u of t. Now I'll just try to plot this input and see how does it compare to a first order system. In a first order system, omega z, purely first order system, a low pass first order system, omega z was at infinity, but for this system omega z is at a finite frequency. So we'll see what is the difference. So first we'll plot the input. Again, for this example, I'll assume h of 0 is 1, okay, and the slope of this is m. If I try to plot the response of a first order system, that would be delayed by tau seconds, okay, where omega z is infinity. I'm plotting for the case when omega z is infinity, and the output would gradually reach the delayed version. Okay, so here it will be m, again the slope will be same as m, okay, but the output will eventually try to reach t minus tau into u of t. Here there is a difference. It's getting multiplied by a term 1 minus omega p by omega z. So we'll have to plot this for two different cases of omega p and omega z, okay, or three different cases. So first we'll plot it for omega p less than omega z. Okay, when omega p is less than omega z, 1 minus omega p by omega z is going to be less than 1. Okay, so what's happening is that this graph, instead of the final value being t minus tau, it's going to be t minus this term. I'm going to call it as some x. It's going to be t minus x tau, where x is less than 1. So this is, I'll write it as tau into 1 minus omega p by omega z. Yeah. Here omega p is less than omega z. So your tau occurs here. Okay, but this value is here, so the output would be something like this. Okay, so first order system would have taken a path, a purely first order system without a 0 would have taken a path like this, but now this system has taken this path. With a 0 it has taken this path. Now you can intuitively see in the steady state what exactly is happening is that the delay is reducing. The delay is reducing compared to this. Initially the delay was tau seconds, now the delay is tau into 1 minus omega p by omega z. Now when you assume omega p equals omega z, exactly equal to omega z, then both the functions would perfectly overlap. In fact, that is simply a case of pole zero cancellation. So there is no delay in the system at all. Okay, but for any finite omega z, it's going to reduce the delay. It's going to behave. It's going to behave as though the system has been speeded up. It's going to behave faster than a single pole system with no zeros. Okay, by adding the 0, we are enhancing the speed of this. We are enhancing the response time, or the delay is reduced. You can see it that way. Okay, otherwise the behavior is identical to a first order system. The only difference occurs in the steady state error also reduces. You can show the steady state error will be m into tau into 1 minus omega p by omega z. Okay, when omega z is exactly equal to omega p, the steady state error becomes 0. That's an obvious case of pole zero cancellation. It's just a constant function. The gain is just 1 for all frequencies. Okay, but for any other omega z which is greater than omega p, the error will reduce. Initially it was m into tau, it will reduce by a factor given by 1 minus omega p by omega z. Okay, now we will draw for the case when omega p is greater than omega z, or your 0 occurs first. And if you remember, I'll just say a point here. For this system, it's a lagging phase system. The phase will always be less than 0. We already plotted the response of this system. So essentially this system starts from h of 0. First it encounters a pole and then a 0. The phase function was always negative. We plotted this in one of the previous lectures. It was always negative. So output should always lag the input. That's what we said. And we can see it here. Now, I'll try plotting what would happen when omega p is greater than omega z. So we know the output is m. I'll assume, again for this case, I'll assume h of 0 is 1. It's easier to plot. M into t into u of t minus 1 minus omega p by omega z into tau into 1 minus e power omega pt into u of t. Now this term, since omega p is greater than omega z, this term is going to be negative. So I can replace this, I can make this as positive. Okay, and then because your omega p is greater, I can actually, or let me just write it this way. So omega p is greater, so this would be positive. Yeah, so you can write this expression like this. Now to plot this expression, what I would do is that first we'll plot the input, and if you look at this in the steady state, this input reduces to m into t plus tau into omega p by omega z minus 1. Okay, it's like an advancing system. Okay, so the output, this term, if it's nothing but I'm just taking a linear ramp. If you look at this mathematically, it's just I'm taking a linear ramp and I'm adding some function which is increasing, which is asymptotically reaching a steady state value. Okay, so your system output would actually reach something like this. Okay, and it will look as though your system has been advanced by, here this is negative, so this, it will be tau into omega p by omega z minus 1. Okay, with a minus sign. It will look as though the system has been, output has been advanced compared to the input. Now here I have assumed h of 0 is 1, and so h of infinity is obviously greater than 1, because for the system 0 occurs first, so h infinity will be greater, is greater than 1. So you can't realize such a system where your output will be greater than, will lead the input using a passive circuit, so you have to realize it using active circuits. Okay, so this will be an advancing system, and we know again from the phase response we can see that the phase will always be positive for this system. When your omega p is less than or greater than omega z, the phase response, so this system will look something like this. Here I've assumed h of 0 is 1, so I'll plot 0 dB, you encounter 0 first and then a pole next, and your phase response will always be greater than 0. Okay, the peak will be at omega p, root of omega p omega z, and 0 is first and the pole next, so the high frequency gain is always greater than 1. And we can very easily see at origin, at t equal to 0, the rate which is the input is going to rise will be higher. Okay, in the steady state, of course, it's going to catch up with t into u of t. That is determined purely by the DC gain, which is equal to 1. So it will be same, and the slope will be same in the steady state. But at t equal to 0, it will look as though the input is rising faster. The output is rising faster. Sorry, the output is actually rising faster, because of which it will have a head start. This will be leading the input, and the error, the steady state error, will again be given by m tau into omega p by omega z minus 1. Okay, so that's the response for an an advancing system, or where your 0 is less than the pole. So in any practical system, a passive circuit system, what would happen is we will ensure that h of 0 is less than 1, so h of infinity, such that h of infinity is also less than or equal to 1. Okay, so such a system will give a response like this. So we can actually take a small example of a circuit which is of this form, and another circuit which is of this form. Okay, so both these circuits we can very easily write the transfer function. So for this, the transfer function is, the DC gain is 1, h of 0 is 1, h of infinity is half, and the pole occurs at, so I'll write the DC gain, so 1 into, there is a 0 in this system which is SRC, it will be at 1 by RC, and then the pole will occur at 2 SRC, so it will be 1 by 2 RC. Okay, so this is a system where your pole is less than the 0, so this is a lagging phase system. Okay, so when you plot this output, so now if you also so now when you see this, the DC gain is actually 1, so eventually the slope of the output will also be 1. Okay, same as the input. So if I assume I've fed an input of type m into t into u of t, the slope will also be same. But the instant you apply the input, what would happen is that the circuit would behave like a simple potential divider with a gain of half. So if the input is raising with a slope m, the output will raise with a slope of m by 2. It will be half. Okay, see, assume if it was purely a differentiator, integrator circuit like this, wherein a single pole system which was just 2R in series and capacitor. I'm just taking this circuit, the poles are same for both these circuits. This would have risen with a slope, which would have risen parabolically, the slope would have been 0. But because you are placing a 0 in this circuit, the initial slope is finite and it is actually lower than the input, which is given by m by 2. So this is what is helping you reduce the delay. Okay, for this system the delay tau would have been 2 RC. Now in this system we can actually show the delay will be tau by 2. Okay, the final delay, so when I'm plotting the output, so this point is actually tau into 1 minus omega p by omega z. Omega p is 1 by 2 RC, omega z is 1 by RC, you will get tau by 2, and eventually the output would catch up to the steady state value, and the steady state error is also m tau by 2 in this case. Whereas in this system, see, I'm comparing two systems with the same poles, the steady state error would have been m into tau, okay, which is 2m RC. But in this system the steady state error is simply m into tau by 2. Okay, for this system h infinity is 0. Okay, high frequency gain is 0 because there is no 0 in the system. Now adding the 0, what it do was that if, let's say, I'll try to plot the input of this input, the output of this system on the same graph, that would have been something like this. it should have been for tau seconds, but because of the addition of the 0, this delay has been reduced to tau by 2. Okay, and you can see intuitively in this circuit what happens is that instantly when the input is applied, the capacitor here will behave like a short circuit. The output is 0, but here the resistor will take there will be a resistor at the output which will give you a gain of half. So the output actually rises. It doesn't rise parabolically, but it rather rises linearly at t equal to 0 with the slope of m by 2. Okay, because of which it will eventually, because it's rising quicker at t equal to 0, eventually steady state value, the slope is same as the input, so the steady state error also reduces. Okay, compared to the pink curve, this one rises faster at t equal to 0. That's why it has a head start compared to the pink curve, and that difference is always maintained. Okay, so now similarly, when you assume this circuit, which is actually, consider this circuit which is purely a passive circuit, again the DC gain for this is half, and it has a 0 at 1 by RC and a pole at 2 by RC. So the transfer function is this. You can very easily show this. We have already discussed how to find the transfer function by inspection. Now for this function, now we see that the 0 is at 1 by RC and the pole is at 2 by RC. So 0 occurs first. Okay. Now the moment you apply the input, the instant you apply the input, so to actually plot the output, we need to always look at the steady state value first. The steady state value, the steady state is the DC gain, which is half. So if your input is increasing with the slope m, which is m into t into u of t is your input, the output is going to be half of this slope. This will be m by 2. Okay. So to plot the response, I can't compare it to the input, rather I'll plot it with the output. So here I've not shown it to scale. I've assumed the slope of this is m by 2. Okay, it is m into h of 0, which is half. Now we will plot with respect to the steady state output. So this is the steady state output. Okay, how will the response look like compared to a steady state output? Now we know, because it has a pole and 0, the 0 occurs first and the pole later. So the response is going to look something like this. Okay, and we already discussed this will be this output will actually lead the steady state value. The output will actually lead the steady state value, and this time tau, it's actually omega p by omega z. Okay, so omega p is 2, so you will actually have so in this case I think I should write here tau is actually RC by 2. Okay, here for this system the tau is actually RC by 2. So here you would actually have tau into omega p by omega z minus 1. Okay, so it would be omega p is 1 by RC by 2 and your 0 is this. So you'll actually get tau, which is RC by 2. You know, this term will be RC by 2 here. Okay, the important point here is that the system is actually leading the steady state input, and that comes because your 0 is less than the input, less than the pole. Okay, so now you can apply and understand this system intuitively. Intuitively, when you see this, the moment input is applied, the entire voltage, the capacitor will behave like a short circuit. The entire voltage will appear across the resistor. Okay, so the slope, initial slope, will actually be m. In the steady state, it's just going to be R and R. You are going to have a simple resistive divider circuit. So the slope is going to be m by 2. So eventually the slope is going to be m by 2. But because the output had a head start initially, because it was rising faster, it was rising with a slope of m, it will actually lead the steady state output, which is simply m by 2 into t into u of t is the steady state graph. The output will actually always lead this. Okay, and mathematically we have seen how to compute the value by which it leads. We can actually substitute in those equations and find that out. Okay, so this is about a positive 0. So now we will consider the case where we have a right of plane 0. So 1 minus s by omega z, again this is a realizable transfer function, into 1 plus s by omega p into h of 0. So I'll directly write the final result. Since we have gone through this, if I apply an input m into t into u of t, so you'd actually get m into h of t into t into u of t, okay, minus 1 plus omega p by omega z into tau into 1 minus e power omega pt into u of t. Again, you can very easily show this result. We have already discussed it for one case. The minus here is replaced by plus. So which means now we know that the phase is always lagging for the system. It's always negative, because of which your output can never lead the steady state value. It will always lag. And in this system, because of right of plane 0, this is your steady state graph. If let's say you had no pole, no 0, in that case it's going to be delayed by tau seconds. But because you have added a 0, a right of plane 0, the delay is going to further increase, and this delay is going to be tau into 1 plus omega p by omega z. Okay, so if omega p equals omega z for right of plane 0 system, this is going to be 2 times tau when omega p equals omega z. Okay, so the output is going to look like this. Eventually it will reach this value. Okay, if you had no pole, no 0, it would have reached this way. The presence of 0 is actually delaying it further. A right of plane 0, in the steady state it can be seen as that you are actually delaying it further. Okay, so this is all about first order systems and ramp inputs to first order systems. I'm not even solving an example problem for this, because it's pretty obvious. Right of plane 0 is going to introduce extra delay, and this graph here shows this, that extra delay is given by this function, and this is the steady state delay. Okay, and you can very easily, you can take a standard example of a right of plane pole and 0 being same. So you can very easily show that the output for this is going to be, the DC gain is 1. The output for this is going to be delayed by 2 tau. Okay, there is a slight difference though. The slight difference is that at t equal to 0 for the previous systems, meaning for a simple low pass filter, see, let me just compare it with, I think that is an important point to consider. Let's say I want to compare this to a first order system with a time constant of s2 tau, 2s tau, 2 tau as a time constant. There is a difference. The difference comes at the behavior at origin. For a first order system, your h infinity is 0. Purely first order low pass system, h infinity is 0. But for this system, h infinity is 1. Okay, so h infinity is 1. Okay, but the steady state, in the steady state, what would happen is that at origin the first order system will have 0 slope, but this system will actually have a finite slope. This system, when I say this system, the system with a finite 0, the slope, it won't rise parabolically. That's all I'm trying to say. Okay, it will rise linearly but with a slightly different slope. Okay, so you can actually show that it will rise with a slope same as the input. Okay, it will rise initially, so you can actually show the slope here. So this, if I'll assume a case omega equal to omega p, then this you would get t into u of t minus 2 tau into 1 minus e power omega pt into u of t. Okay, so for small values of tau, this would be t into u of t minus 2 tau into t by tau into u of t. So tau and tau cancels out, it rises at minus t into u of t. Okay, yeah, so I'm sorry, so it actually, the output, I'm sorry, so that it won't raise like this. Even the steady state value is correct, but the graph is not correct. I'm sorry. So let me just plot that response. So essentially what you have is, you have t into u of t like this. the output here is going to reach a value of 2 tau. Here I've assumed m as 1, so let's assume it's m into 2 tau. This will be the steady state value. I'm plotting it for the case when omega p equals omega z and h of 0 is 1. Okay, and your input is this is with the slope of m. Now when you subtract these two functions, this will go to a value of 2m tau. So I think it should actually have a response like this. It will actually go to negative values and then go up. So this is your input. Okay, the delay comes from that, because the input slope cannot be 0. Initial at t equal to 0, the slope cannot be 0 for this system. Okay, so because this is rising initially with a slightly higher slope, which is actually 2t, and this is initially rising at the slope of t. Okay, so when you subtract the two, your response will be like this. I'm sorry, the response will be slightly different. So it will actually hit 0. Okay, and then revert back. Okay, so this is all about first order ramp response for a system with for any first order system with a finite 0 and a pole. So I think I'll probably make a small video in the next video just to discuss about the right of plane 0. How does the response behave at t equal to 0 and when does it cross 0? I think this video is already too lengthy, so probably I'll try it in the next video. I'll stop at this point.